All right, hello. I'm going to go ahead and get started. Today we're going to be talking about activity. First things first, I always like to start things off by seeing where you're at and how you're coming along. So ask yourself, I'm going to share my screen, how you doing in your studies? It's getting close to boards time. I know, Jamie, your board exam is coming up in 2 weeks. I believe Mike D, his exam was this week. Good luck, Mike, if you're seeing this. And Celia is, I believe, the first week of June. So, how have your study plans been going? Have you actually developed a plan? I know some of you guys started like you already made good progress. If I'm remembering correctly, Jamie, you wanted to spend a couple of hours each day studying. You thought you could open up some time to do that, given that you've taken off of work, and stop and reflect. How have you at least committed to a couple of hours, 2 or 3 hours? If so, you know, how are your study methods? Were you getting sleepy? Did you get distracted, or were you focused? Were you in an environment where you could focus, or were you getting um, different requests or bids for your time? And how about the material, the study material? Did you connect with it? Were you able to make connections with your other learning? Did it relate to what you already know? And if not, maybe spend a little time considering just going down the rabbit hole of what's the bigger picture here, and how does this relate to um, the concept of radiation oncology or radiation therapy, or whatever the topic is. That I chose the broadest sense of the topic, of course. You might be studying something way more specific. But stop and reflecting on where you're at can help you shore up any kind of weaknesses or failures that may have happened over the week. Taking stock and then recommitting and doubling down on the time you have remaining can help you prioritize your studies. There might be some studies and some knowledge that you're good at, and you don't need to spend a whole lot of time, going deep into the weeds. But I just want to encourage you guys, don't lose heart. You've got this. I know, Celia, you shared that's overwhelming. There's so much content, and um, sounds like your plan was to dedicate lots of time each day. You can ask yourself, how did you do? The Laura Nappy review guide has been helping you, making notes from that, and then going over concepts that maybe you don't quite understand as well. Um, Hopefully you're digging into the math and continuing to realize math isn't so challenging, which kind of shared last time we were together. Um, we're going to get into some math today, so hopefully this helps. So, radioactivity. Radioactivity was discovered by Henry Becquerel, but something more relevant to radiation therapy, it was really therapeutically valued at the turn of the 20th century. So radium, which is a radioactive decaying matter or element that was found in nature, was discovered by Marie and Pierre Curie. And their unit of measuring radioactivity is still used today in the millicuries. So I'm showing two rocks. Can you guess which one is radium? Radium is the glowing rock. You may have heard of the book in recent years called The Radium Girls, and it's a black backdrop with a bright, radiant green, neon green writing on it, text on it. And it's all about the women of the First World War, and later, maybe even early part of the Second World War, that were commissioned to paint watch dials and electronic dials, like in the aircraft, or the soldiers in World War I and World War II, because before they were illuminated by electricity, they needed some sort of illumination to use their dials and their gauges at night or their watches during night in the battle. And they used the glowing properties of radium to paint the surfaces. And to get a fine tip, they were trained to lick the tip of the brush and be able to paint these small, tiny, detailed areas on the dials. And they were told it was safe, but later it was discovered that obviously it wasn't safe. Radium is, I believe, alpha emitter, and although the radioactive particles are heavy, they do a lot of damage near the surface. And they resulted in many grotesque deaths and problems and comorbidities at the least of these poor women who suffered because of consistent radium exposure. So what about the rock in the upper right corner? Well, that is how it was first discovered, and that takes us into radioactive decay. That rock is called pitchblende, and pitchblende has been around for a long time. No one knew what to do with it, and it was considered refuse. And essentially what pitchblende is it's instant, not instant, but it's like bad luck, because when it was mined, especially in the mine where Marie and Pierre Curie took it from, it was essentially when the miners in whatever mountains they were in Europe would find this pitchblende, they would get it out and move it out of the area they were working with, or they would abandon the area they were working with altogether immediately or very quickly, because miners were known to die after exposure around it. Not just, kind of this weird sickness that we now know resembles radiation exposure sickness. What is pitchblende? But it's actually the decay series from uranium all the way down to lead. And so as we learn in the next point, radioactive decay is actually a phenomenon that happens when you can think of this as pitchblende that has, in any given pitchblende, is you have uranium, which is highly radioactive, right? It's used in nuclear reactors. And you have thorium, and you have chromium, and you have palladium, and you have radium and radon. And each of these are in different transitional levels of decay, because what happens as you have an unstable element, it loses energy, and as it loses energy over time, it turns into a different element. And that's how all these different elements are in this pitchblende. And Marie and Pierre Curie, was actually pretty amazing how they were able to isolate within this massive uranium pitchblende the specific radium from the rock, and actually be able to have applications for it. And it became crazy, like very wildly popular for therapeutic effects, whether they were true or kind of marketed by not so reputable, they call them quacks. But throughout the early 19th century, they used it also in more upright ways in the form of brachytherapy. And it could be used, and they discovered pretty successfully, in killing cancerous lesions. And in some cases, at least in that time in history, during the early 20th century, it was more effective than many surgeries that left people with disfigurement, or even worse yet, death upon the surgeon's table because of, or after the surgery, because of infection risk, or the very what do you call, just very difficult way they had to extract the cancer. They just didn't have the technology and the tools that we have today. So anyway, radium was used on the surface very easily. If they saw a skin cancer lesion, they would apply it to the surface. They noticed that the skin cancer would disappear. They applied it intercavitarily and interstitially. And we'll go to the next slide here. This is the radioactive decay um, process from uranium all the way to the stable element lead. So lead 206 being I believe, the stable elements. And you can see it transitions from uranium and radium somewhere in the middle. Each of them have what we call half-lives. So we can't, when we have a piece of rock, imagine like pitchblende, we can't pinpoint the exact atom that's decaying to this particular, that will decay any second, but to whatever element. But we can say that in a quantity of atoms, there's a certain percentage that will decay to another percentage. And basically, a half-life is the amount of time required for the isotope to decay by 50% of its radioactivity. And here are a lot of popular brachytherapy isotopes. We have radium 226. You can see its half-life is listed here as 1,602 years, although I have other sources that say it's 1,622 years. I would use the 1,622 because that is, I'm gonna notate maybe. Because that is what is in my physics book for radiation therapy physics. So I would trust that. And then we have cobalt of 5.27 years, cesium 137. There's also cesium 131, so don't get those confused. 30 years, 9.6 days. Notice the difference, right? Big time. And it's just a matter of the isotope, right? You have iridium 192. And what I like about this chart is it also shares with you how they decay. They decay through gamma emissions, right? And the gamma emissions look like a symbol like that, and beta emissions, and they look like a symbol like that. And I don't see any alpha. That's interesting, but alpha would be something like that. And oh, that's cool. It also includes the half value layer. I wonder if we'll be calculating that later today. Um, I left off with iridium 192. You can see that as 74.2 days. It's actually commonly used in HDR brachytherapy or high dose rate brachytherapy for prostate, very common. Strontium 90, phosphorus 32, radon 222, gold 198. I think these are also I don't know. I don't know how gold 198 is used. I was going to say it's used in brachytherapy, but I'd have to confirm that. And then iodine 125, I believe these three are used primarily in LDR brachytherapy. So here's a quick picture of a radiograph of prostate. You can see all these tiny little radiopaque lines, or they're what they are. They're seeds in the prostate that have been inserted through the perineum and deposited there. And these are permanent. They're not temporary. So this is LDR. It was pioneered in the 1960s. Very commonly used LDR sources, like I mentioned, cesium 131, iridium 125, and polonium 103. And so with these, they actually are planned to decay at a certain interval of time, at which point, when they're done irradiating, then the cancer will be cured. I think that is pretty elegantly simple, if you ask me. There are, you know, side effects known for this that could cause, you know, maybe not everyone would choose this solution, but it can be a very simple and elegant solution that can cure the cancer. And it's one visit. You might be sleepy under like a twilight anesthesia, or you might be not, put to sleep under full anesthesia. And they go through the procedure of putting these radioactive seeds in. So, whoever's doing this, right, physicists would be involved, but it requires understanding half-lives, right, and how much activity and dose would be put or absorbed into the prostate and also surrounding areas. So since these are gamma emitters and they do travel further than beta and alpha particles, they still, you know, have an added benefit of being emitting a certain area from where they're placed. So they won't have, they won't give exposure, significant exposure at least, to the peripheral areas, whereas external beam would. Anyway, so on the right, HDR, that's the HDR machine with a bunch of like cords. Those aren't power cords, those are actually tube-like catheters that are inserted. In this case, if you were to do an iridium 192 HDR procedure on a prostate patient, they would go through the perineum with the catheters and keep it open, and keep that person sedated. And then once it's been programmed in the machine, a set number of radioactive sources would travel down the tubes and into the location, the terminal location of where they've planned, and essentially remain there for a short period of time, and then retract back through the catheters and into the afterloader machine. Most often, the source used for this is iridium 192. And occasionally, I think the patient would maybe do one trip, or maybe they would do multiple trips to the center. I don't know. I don't have any experience with it, actually. So I don't know if it's one trip and you're done, or if it's multiple trips, like maybe 3 or 4 trips over a course of time. It might be one trip in a week for maybe 5 or 6 weeks. Really don't know. But this talk about half-lives brings us to the half-life chart, which is neat. You don't actually need to memorize this chart. It's all you have to do is have a little handy dandy calculator wherever you're at. So if you're in the board, all you have to do is divide, 100 by 2, and you get 50, and that's one half-life. And then you take 50, right? And you divide 50 by 2, and you get 25, and that's another half-life. And this is important, or this is relevant, because oftentimes you get questions on the board. This will come up on your board. It's like, how many half-lives does it take to reduce the activity to under 5% or something like that? And so if you don't know it, that's okay. You can just simply keep going, and you take 25, and you divide that by 2, and you get 12.5, right? That's your third half-life. Well, we're still not under 5%, so let's try it again. What's 12.5 divided by 2? Well, it's 6.25. Okay, well, that's your fourth half-life. That's still not under 5%. So we're going to divide that by 6.25 divided by 2, and that equals 3.125. That's your fifth half-life, and that is under 5%. Voila. So you can memorize, oh, it takes 5 half-lives, to for the activity to decay to less than 5%. Could remember that. That's probably pretty easy. It's 5 and 5, right? Or if you know you don't want to commit it to memory, it just took, what did we take, 30, 40 seconds to do this? All right. That's awesome. So this is the end of kind of my background on radioactivity, but I want to get into the homework problems or the practice problems that we did, or that hopefully we did, right? Did you do them? Did you do them, guys? I'd like to go over them with you guys. So we'll start with activity, and since that's the topic of today, then we'll kind of go back through the practice problems. So I think this is going to be a great place to start. And you might recognize this. So let's read it together. It says, how many half-lives would it take for a source of cesium-137 to reduce to less than 5% of its original value? How many half-lives would it take for a source of cesium-137 to reduce to less than 5% of its original value? Oh, that looks familiar. You start at 100. How many half-lives to go to less than 5? So we know actually the answer is 5 half-lives. This can be worded by, in general, just like the question might be, how many half-lives will it take any radioactive source to decrease to less than 5%? Or it might say a specific source. And then the reason why I bring this up is I don't want you guys to get like focused, laser focused on whatever source that they put in here, because it's a red herring, or it's something that could potentially distract you. It doesn't matter what source it is, because we're just talking from what percentage, how many half-lives can we go from 100% to below 5%? So we're talking, how do we go from, how many times do we need to divide by 2 in order to go from 100 of something, of anything? It could be cesium 137, it could be iridium 192. It doesn't matter what that something is, it does not matter. But we're going to go from 100% of something to 5%, less than 5% of something. So the problem that I see happening probably is someone might say, oh, I know what cesium, what is cesium? Well, we can look it up, right? I'm going to delete. Cesium 137 is 30 years. Someone might say, oh, I know how many, I know the half-life of cesium 137. It's 30 years. And is that true? Did I look that up right? 131. Yeah, cesium 137. Yeah, 30 years. Um, and they're like, oh, and then that you could accidentally go down the rabbit hole of like dividing um, 30 by 2 and getting 15, and then 15 by 2, and then you're getting 7.5, and you just keep going down that rabbit hole. And that's not the right way of doing it. We're not, unless it's asking you, um, you know, a specific, you start with a specific amount, maybe like 200 millicurie of cesium 137. And how many millicuries, maybe the question is, how many millicuries remain after 5 half value layers, then, you could calculate that in that way. All right, let's move on to the next one. All right, so this one, what percentage of radioactivity remains for an iridium 131 source after 8 half-lives? Oh my gosh, now we can practice. But I'm kind of curious to know if we can do what I suggested or if we need to use the formula this book suggests. So I'm gonna try something. Let's see. So what is the iridium 131 half-life? Just curious. Let's find out. Iridium 131. Oh, iridium 192, my bad. 74.2 days. That's what I have here. Interesting. This source has 73.8 days. I'm going to refer to um, my physics book of 73.8 days instead of the 74.2. So half-life for iridium 130. Wait a second. That says iridium 131. Did I write this wrong? Nope. Okay, so maybe that's. Oh, interesting. You guys may have already picked up on it, but I was looking at something different. Okay. So, is it? It's I wrote this problem wrong. Iodine 131 is what it's supposed to be according to my book. That's why I'm getting different things. So sorry, guys. It's supposed to be iodine or and the half-life for that for iodine. Oh, this one only lists iodine 125, but have no fear. The physics book that I have has the half-life of iodine is 8 days. So I'm kind of curious. There is a formula to do this problem, and we'll walk through that formula together. But I'm curious to know if we can do this little method of dividing and dividing and dividing and dividing by 2. So we know there's 8 half-lives. Huh. So what if it's not interesting? So it's not asking for the activity. It's not asking for the millicuries. It's just asking for what percentage. So given that, it's actually another. variety of the last problem. It's basically, we're going to go from 100% of something. In this case, it just so happens that it's iodine 131 isotope, but none of that matters because we're just going from a percentage to what is the percentage after 8 half-lives. That's all the question is asking. This is a question mark. So I think we could solve this without a fancy equation because all it's talking about is the percentage and half-lives. So we'll just do our little handy dandy trick. We'll start at 100 and we'll divide it by 2 and we'll just count. We got 50. It's like being on Sesame Street with the count, and he's 50, And then you take your 50 divided by 2, and you get 25, And then you get 25 divided by 2. Come on, everybody, sing along, or do it along with me. It's 12.5, All right, I promise I'll stop. We got 12.5 divided by 2 is 6.25, and that's the fourth half-life. Still not to the eighth half-life yet. We got to go all the way to the eighth. So I'm gonna have to start like bringing out my calculator. 6.25 divided by 2 equals 3.12. What is it? 3.125. We'll just call it 3.125. So that's the fifth half value layer. We're gonna bust out my calculator. And I get 1.56. That's the sixth. Oh my gosh. I'm gonna take, no, I'm gonna take this, come up here with it. So we're gonna take 1.56, divide this by 2, and 0.78. Oh, we're getting close. I think we can do it. 0.78. And that is the seventh half value layer. And then we're going to take 0.78 divided by 2, and that equals 0.39. That's the eighth half value layer. No, I keep saying half value layer. That's the eighth half life. So sorry. Oh, that's one of the, so that's right. I mean, that's a decimal. And if you start at 100%, you wound up all the way over here. What you would do is, I think you would multiply that. Yeah, so this is basically all percent. You don't have to multiply anything. It's all percent. I should have left the percent sign so we don't get confused. Um, your answer is a percent. So that answer is letter A. Ding, 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 ding. That is the correct answer. Now I'm gonna go through working out the equation. There's an actual equation that you can get this answer so much quicker. Maybe you're going to enjoy this, or maybe it's just going to be another thing to remember, and that's going to be annoying. So you might actually find comfort knowing that you don't need to remember a fancy equation. You can just do the work. Dividing by two for the number of half lives, excuse me. So let's erase this. All right, so what percentage of radioactivity remains for an iodine 131 source after 8 half-lives? So one thing, there's really this really fancy equation that we can use. And that fancy equation is current activity equals the initial activity times half the exponent of the half-life. The not so said it's the half-life, that's not correct. It's the number of half-lives. So in this equation, it's 8. So it's asking what is the percentage of radioactivity that remains after 8 half-lives, n being the number of half-lives. I'll go ahead and write this in. That is the initial activity and the new activity. And in this equation, we will be multiplying by interesting, 100%. Cool. Why? Because we're talking about percentages here. And we're actually, oh, I'm so bad, but we're not actually, so there's a variety of derivations of this formula. Another derivation is n, but n can be substituted. Oh, that's not that. N can be substituted by this exponent. The exponent is t, where t is the elapsed time over the half-life. So this is the half-life. So the half-life in this example, this is the elapsed time. So that's another derivation of it. And we're not going to get into how we would go from here to the number of half-lives because the truth is, I don't really know, and don't know that it really matters. Um, Basically, my understanding is that this ratio between elapsed time and what is the half-life equals, so T over T half, that equals the number of half-lives. So maybe that, if I were to put that in numbers, if the half-life of iodine 131 is 8, in order to make the number of half-lives be 8, we would have to have what, 64 or something like that. So maybe the elapsed time would be 64 days. Half-life is 8 days. Therefore, you have 8 half-lives. So none of this really matters. And the problem didn't give you any of this. I'm just trying to show you how um, it could be related. So the question could be reworded something like, after 64 days, iodine 131 maybe it would be reworded like, what is the percentage of radioactivity or iodine 131 experiences after 64 days? What is the what percentage of radioactivity remains for iodine 131 after 64 days? And they would, with that, you'd have to then kind of plug your numbers in. You'd have to put in, okay, well, it's 64 days divided by, I know the half-life of iodine 131 is 8. So after I do that, I know that 8 half-lives have passed. Like that's how that, so basically the way this question is written might be a simpler format than what the board might give you. Although I gotta say, I don't think the board is super concerned about radioactivity. It's important, and these concepts of what to do with some of these numbers and how they relate, I think are important to know. But I don't think it's worth worrying about, so to say. Like, I just want you to see how, the T over T, so the time elapsed time over the half-life time is equal to the number of half-lives. So you feel more comfortable using this formula rather than because maybe seeing how they relate, you might say, well, I'll just remember one. Instead of remembering both formulas, I can just remember one. I'll just remember this formula here. A equals the initial activity half over T and T half. Boy, that's confusing looking. I'm so sorry how I write. It's an exponent, so I want to make sure I write that better. It's T over T half exponent. And so maybe that's the only one you remember. And then you're like, okay, I know if I get a simple format, and it just gives me the number of half-lives, then I can just substitute it with N. Or if they don't give you the number of half-lives and you have to actually do something with the information they give you, for instance, like the second example I gave you where they say, what is the percentage radioactivity that remains from an iodine 131 source after 64 days have elapsed. That very well could be a board question. That could. And so from that information, kind of going back what I kind of was mumbling out up top, is that you kind of have to know what to do with this. And we didn't even get into what to do with that, right? No part of either of these questions have anything to do with millicuries, which is what the activity would be labeled as. So because of that, since we're just asking for the percentage in this equation, A is actually irrelevant. We're not asking for the activity, we're just kind of hijacking the equation. And that's where the 100% comes in, actually. So it's unique to this hijacked equation. So we actually get rid of the A naught, or the A subscript 0. We just have half. That's times 100. 100 is what gives us the percentage. So that's kind of, it's a long story. That's where I want to take you, is how you can use this equation to figure out this problem. And so what that is, if we'll just do this second problem here. So what is the percentage of radioactivity that remains from an iodine 131 source after 64 days have elapsed? So T is elapsed days. So I'm going to rewrite this. So we have half, and that is 64. We from, let's see, if we were to look, did we already say it's not on here? Oh yeah, it's not on here. How quick I forget. The 131 iodine half-life equals 8 days. So that would be something you would commit to memory for the board exam. You might actually commit, sorry, I know you can't see that, but you might commit all of these to memory, right? Radium 226, cobalt 60, cesium 137, iridium 192. Strontium, I don't think you need to commit that to memory. Phosphorus 32, I don't really think that's that important. Radon, don't really think that's that important. Gold 198, let's do that. Iodine 125, smart. Palladium 103, maybe. Cesium 131, smart. So making sure that you know those, I think, is important. That way, if there is a question on the board exam where you might have to, and that might be something you have on a cheat sheet that you develop, where you might memorize the things on your cheat sheet and then be able to kind of regurgitate that by memory upon starting the examination. In other words, you just kind of brain dump, equations and stats, like for instance, these statistics or these data. And you might brain dump that initially, like right up front, so you don't have to have the load of that mental energy just trying to hold on to all that. Meanwhile, you're reading and really contemplating 225 questions or 220 questions over the course of an hour and a half to 2 hours. So that's what I would do if I were you. Back to this. So to solve this second kind of problem, the way it's worded, you'd have to know what the half-life is of iodine 131. So we know it's 8 days. So we plug in the half-life is, make sure your units are the same, right? So they told us 64 days. If they had given us, oh, if they had given us like um, maybe 6 weeks or something, we would have to convert 6 weeks to days, you know? So it's just one of those things that you always want to make sure you keep your units the same. Of course, you'd have to, like I said, you'd have to convert weeks to days to get the units the same. And I think getting the units to whatever your half-life is the way to go. Because, I mean, alternatively, you could just convert, your half-life, which is in days, to another unit. But I think it's nice working with whatever your half-life is. So if your half-life is years, convert, whatever you have up here to years. And the way you do that in this example would be you have 365 days equals 1 year. And if you're going, so I put that in the form of a ratio because basically 365 days over 1 year is the same thing. So I could put that into a ratio, like for instance, I start with 64 days, and I want years, maybe. I have like a format, but if I want years, I circle it, put it in question marks. I start with days, and then I just begin kind of cross multiplying. So I know that I need to go to a year. I want year to be up top. So I guess I'll just flip these around. So I'll have 1 year equals 365 days. Days cross out. So now I'm dividing. If I were to rewrite that, I would rewrite that as 64 divided by 365. And that's going to give me my answer in years. Because the days cross out, I'm left with years. So if I were to actually calculate that, 64 divided by 365, I would get 0.175 years. Wow. So I'll rewrite that down here. 0.175 years. That kind of makes sense, right? So that's, we would kind of expect how many days to be in the first quarter of the year. Be 3 months, 3 months, 30 days. So maybe 30, 30, 90, like 90 days. He might, so not 90 days is about 0.25. So it kind of makes sense that 60 days is 0.175, right? Because, well, 60 days is less than 90. So it makes sense that 0.175 is less than 0.25. I guess that's kind of how I think about my answers is like I try to relate it to what I already know to see if it makes sense. Does 0.175 years actually make sense? So we got on a bit of a tangent, but I wanted to kind of go over feeling more comfortable with converting units because maybe you don't feel strong in math and you're just like, well, what do I do? I don't want you to get all messed up. You might know how to actually solve this problem using this equation, but if it goes from weeks and you got to go to days, then I don't want you to be frustrated and be like, oh my gosh, it's the one thing I don't know. I'm going to get this problem wrong because I don't know how to convert from weeks to days or days to years. So that's why I wanted to go over that with you. Bless your heart for staying with me. All right, so it's 8 o'clock. I'm gonna wrap up here soon, but we're gonna wrap this up and go over one more. But in this example, you have 64 days, which is what was given to us in the problem, and divided by the number of what the half-life is. So it just happens to be days, thank goodness. And if I were to rewrite that, that would be 64 divided by 8 is 8. And if I'm going to punch this in the calculator, I might rewrite half as 0.5. It's the same thing, right? 0.5 is the same as half, right? Because 0.5 plus 0.5 equals 1. Half of 1 is 0.5. It's magic. I guess not, it's math. Um, don't forget the exponent. Let's type this into the calculator. So when you type it into the calculator, this might be your first time typing it in the calculator. What you're going to do is you're going to first type in 0.5, right? 0.5. And then you're not going to do anything except for look for the button that is an exponent button. The button kind of looks, this is a picture of a button, kind of looks like a caret. And so you're going to press that button. And then you're going to type in your exponent. In this case, you're going to type in 8. Hit enter, and you get 0.003906, whatever. So remember this 100? We actually should have dropped the 100 times by 100. And that gives us the percentage. Otherwise, we're just left with a raw number. But remember any number, right? So if you had like 0.25, like we had an example of like 90 days is times 0.25. Wait, kind of like we talked about a quarter of a year. So 0.25 times 365 days might be equal to about 90 days. And if you put it in another way, you would say 25% of 365 is about 90 days. So 0.25, the difference between 0.25 and 25% is, to represent it as 25%, you need to multiply 0.25 times 100. And that's how it's represented as 25%. So that's why if it's asking for the percentage, that's what it's asking for. It says, what is the percentage of radioactivity? That's why we need to throw in the 100 to get the answer as a percentage. So yes, this is the numerical answer, but to get it into a percentage, we need to take 0.0039, we'll just round it to the fourth, the 10,000th place, times 100. And that gives us, and what do we do with that? Well, we just move the decimal place over to get a bigger number, which is point, because it's the same thing we did here, right? When you multiply by 100, you move the decimal place over to the right, and you get 25%. So we're moving the decimal place in the same way over to the right to get 0.39%, which is the answer. Interesting. So there's two ways to get the answer, right? There's the formula, A equals A naught over t, that exponent. So you can just remember this formula and you're good to go. You just have to kind of know what to do with the formula. Or you could just start at 100, divide by 2, get 50. Take that, divide by 2, get 25, and do that 8 times. And then you get 0.39%. So all of these are percents. So maybe that's more simple. So we kind of started with the more simple, right? You just divide things by 2, you divide 100 by 2 8 times. Or you could just do some derivation of this formula. Hope you're not confused. I hope you're not intimidated. I kind of wish you were here so I could answer some questions because I feel like I could do better with the dialogue. All right. You're still ready and willing. We got more. Just one more. Let's do it. So there's two formulas. So this is going to be completely going to move on. And all right. Blank screen. Here we go. There's two radioactivity formulas. We already saw one of them, right? That was the one you may not have liked. So there's formula number one. Then there's formula number two, and that's related. And what this formula does, it helps us get the new activity. And we can also rearrange it to get the percent radioactivity left. That's what we kind of experienced. With formula number two, that formula is very similar looking, but it's got one key difference, and that is it has the decay constant multiplied by the source's half-life. So it's represented like this, very similar, but slightly different. It's the new activity equals the initial activity, or A naught, multiplied by the natural log. I'm going to write ln, because that's how it's represented in your calculator, as ln. In formulas in books that you read, it may look something like this, L naught E, with an exponent of lambda, which is the decay constant times the half-life, or T. So that's the way some textbooks will write it, but I'm writing it in a way that I think will be hopefully useful to you. So it's the natural log of negative lambda times the half-life. What in the world is this used for? Well, if we're given a decay constant, for dealing, we'll see if we can come up with a formula that how we're going to use this formula. So I'm going to write out a practice problem. Call it practice problem number 1. So a radioactive isotope, this is the problem, starts with, ooh, we're going to get into activity, starts with 10 millicuries. What is the activity after 20 days? If a if it has a half-life of 60 days. That's the question. So a radioactive isotope starts with 10 millicuries. Wants to know what the new, what is, so remember what is this one? It starts, that's the initial, right? That's what it starts with. That's A naught. So A naught equals 10 millicuries. But the question wants to know what is A? What is the new activity? That's the question. I always like to start my solving these with what does it want? Because there's a lot you can do with the information sometimes. And what helps you focus is knowing what it wants. And what it wants is the question begins, what is the activity? So, what is the activity after 20 days if it has a half-life of 60 days? Well, that sounds an awful lot like problem or equation number 1, right? Equation number 1 is activity equals the initial activity times half, and it has elapsed days over the half-life. Because what we're given after 20 days, that's the elapsed days. And it gives us a half-life, so of 60 days. Okay, so now we can start plugging things in. We actually have a lot of good information. So we have the initial starting activity, we have the elapsed days, and the half-life. So plugging that in, we can do 10 millicuries times half with an exponent of the elapsed days, which is 20, divided by the half-life, which is 60 days. And you can label days, but days will cancel out, so you'll be left with no units. So the next step of the problem is let's go ahead and just solve this fraction, right? So we'll drop everything else down. When I do a parentheses like this, I hope you understand that I'm multiplying 10 millicuries times half. And then the half has an exponent of 20 over 60, which 20 over 60, written differently, is 1/3. Or let's write it as a decimal. Is it 0.33? I'm literally doing 20 divided by 60. Yes, and it's 0.33. And that is, I'm doing that. I'm not doing 1/3, even though I guess I could, but I'm going to eliminate the fractions so that I can input them in my calculator more easily. Um, so let's go ahead and just do this bit by bit. So you might be confused, like, okay, well, what do I do? Do I do the multiplication first and then the exponent? Do I do the exponent first and then the multiplication? Like, where do I start? Because depending on where you start, you can get a different answer, right? So what if you started just left to right, like the way you read? What if you started there? So then you'd have 10 millicuries times half, right? Well, that's 5 millicuries. So all of a sudden you have 5 millicuries and you do to the exponent of 0.33 and you get an answer of, oh, this is for demonstration purposes. I'm really not trying to confuse you. I want you to know that there's a correct order in which to execute this equation. So 1.7 millicuries is this answer. But if I do it with the exponent first, then I have the equation looks something like, right? It's like 10 millicuries times, we're going to rewrite half as 0.5 so I can input it in my calculator more easily. So that's basically this step just rewritten. I don't want you to get lost. That's all it is. And we're going to change the order in which we execute this, right? So we're going to do the exponent first. So what is 0.5 times 0.3? No, I did that wrong. 0.5 to the 0.33 exponent, and I get 0.7955. We're going to round. I'm going to round to the 10th place. I'm going to round to the 10th place. So I'm going to call it 0.8. And then I have 10 millicuries. I'm just dropping that down. That's all I'm doing. And as you can see, I actually get a way different answer. I get 80 millicuries. One is 1.7 millicuries and the other is 80 millicuries. Completely different. And ask yourself what makes sense. Because what if this happens to you on the board exam, right? Always ask yourself, does my answer make sense? So what if we went with the first route? Okay, so we start with some initial activity and then it goes to a small activity. All right. Oh my gosh, did I do it wrong? I think I lost my decimal. It's not 8, it's 0.8. So I'm so bad. I multiplied it. You probably caught it, but I multiplied it incorrectly. So I didn't do my math on my calculator. I multiplied 0.8 times 10. I should have moved my decimal place over to the right by 1. Instead, I moved it over by 2. So 8 millicuries. That's the answer that this equation would generate. 10 millicuries times 0.8 will give 8 millicuries. Still totally different, right, than 1.7. But the reason why I paused and I caught it is because I know I'm going from a large activity, A naught, to a small activity, which is the new activity, right? So I'm looking for big to start with and small to end with. So they both have actually big to small. So it starts with 10 millicuries, and in one example, it winds up with 1.7 millicuries, and another example, it ends up with 8 millicuries, which both if you asked me, like I probably wouldn't have a good intelligent guess as to which it would be. Although I would say that, plotted on a chart of over number of days, as days go on, the activity, if it starts off at 100, would probably, look something like this, something like that, where, if this is 60 days here, then you have, 40, 20 here, 40 here. It kind of makes sense. Like if you started with 10 and you're at day 20, it kind of makes sense that you're at 8 millicuries as opposed to somewhere down here at 1.7, right? 1.7 would be closer to the 60 days, right? Because it's the amount of activity remaining is much less. That would lead you to believe that the number of days elapsed is much closer to the 60, or even past the 60, right? Because half, oh my gosh, I'm so sorry to take you down this rabbit hole, but like half of 10 is 5, half of 5 is 2.5, half of 2.5 is, I guess, what? 1.25. So what I'm getting at is how many half-lives have elapsed? One half-life, two half-lives, three half-lives. So what that means is it would take, I'm kind of glad we're going through this, although it sounds like a lot, but another 60 days would be half-life number two. So you'd be at day 120. And the third half-life would be another 60 days. So that would be day 180. And you would expect 1.7 to be past day 120, and it would be before day 180. So you'd expect it to be like somewhere maybe like there or something. So what I guess I'm saying is like to wind up with 1.7 is probably not the right answer, because we know that only um, we know that less than one half-life has has elapsed, right? Because we know 20 days have elapsed. 20 days is less than one half-life, which is 60 days, right? So we know that the number of millicuries needs to be greater, the answer needs to be greater than 5 millicuries, because it's less than one half-life. Whew. So this answer is 8 millicuries. I could have just told you that, right? We could have been done 20 minutes ago. But I wanted you to think through the rationale of what makes sense. You could do the order of operations completely wrong, and you could get the wrong answer and never know it, because odds are the board exam probably will have one of the multiple choice answers be the most commonly answered incorrect answer. Does that make sense? Like they'll probably plan for a certain number of people to not know how to execute the order of operations in math, and therefore give an answer that is commonly done incorrectly. But if you would think about it, you got this answer because maybe you did the order of operations incorrectly. You get 1.7 and you'd ask yourself, let's see, 20 days have elapsed. How many half-lives? Well, less than a half-life. Well, if one half-life elapsed, I would have 5 millicuries. So is my answer greater or less than 5 millicuries? My answer is less than 5 millicuries. Therefore, it has to be incorrect. It cannot be correct because less than one half-life has elapsed. So I hope that has helped you. And therefore, I think it's worth maybe spending just a little bit of time here going over the order of operations. So the order of operations is it pertains to solving math problems. It starts with parentheses. So first we do parentheses. Second, we do exponents. Third, we do multiplication. This would be like a number to the I don't know. I just put E for exponent. And then D for division. A for addition. And S for subtraction. And some people will actually kind of remember this as an acronym. The acronym is not super helpful. PEMDAS. But it gives you something to hold on to. Or you can do, ooh, a way, I forget how to, it's like there's a name for it. I can't recall, but it's a memory device. I'll call it a mnemonic, um, where PEMDAS can actually be remembered as please excuse my dear Aunt Sally. Please excuse my dear Aunt Sally. So what does that mean? Basically, if you're given an equation that is, hold on, if you're given an equation like that, what would you do? You kind of realize that B next to this parentheses, it has a multiplication, right? Multiplication. Well, first, what you would do is you would do what's inside of the parentheses, right? Because parentheses is first. So you would first do C minus D, and then you get the answer. And the answer might be, call it E. Oh, this is getting pretty abstract. But C minus D, we'll call it E. So now you have B times E squared. Now what do? You do the exponent. You don't do the multiplication, you do the exponent. There's nothing to do inside the parentheses. Even though there's parentheses here, there's no action to take. So you're going to get the square E, and you might E squared, we'll call that F. So now you have B times F. And when you multiply those, you get the answer. It's very abstract, I'm sorry. But I think you get it. So moving on. I'm going to do practice problem number 2. Practice problem number 2. We'll say radioactive source has a half-life of 36 hours. What is the activity after 4 days? If the source starts with 200 millicuries? All right, so a radioactive source has a half-life of 36 hours. Okay, so it's given us a half-life. Cool. 36 hours. What is it asking? So it says, what is the activity after a certain period of time if the source starts at a certain millicurie? Okay, so it wants to know what is the activity, that's what we want. We want what is A? What is activity? All right. So this is starting to look familiar, right? We have half-life and we also have elapsed elapsed time. So elapsed time is 4 days. And we also have the source starts. It starts, that means that's our A naught, right? So we also have A naught 200 millicuries. Okay, that's looking familiar. That's looking a lot like this formula, right? Okay, well, we know what to do with that formula, right? Because we have elapsed days, which is 36 hours. We have the half-life, which is 4 days. What if we just plug that in, right? What if we have the 200 millicuries, right? So we have 200 millicuries times our half over what? 4 days divided by 36 hours, right? Oh crap, right? This is where we don't have the same units. We have to get the same units. We have hours and days. So this won't give us the answer we're looking for. Let's correct it. So what are we going to do? We have to convert. Let's convert to hours. Let's do hours, right? Because we'll let the half-life kind of dictate. That'll be our anchor. So we're going to go from, that means we're going to change days. Changing days, we're starting with days, we're going to hours. Okay, well, to do that, I got to know how many days or how many hours are in a day. Well, I have one day equals 24 hours. Great. Okay. If I rewrote that in the form of a ratio, that would look like, hmm, let's see, it would look like 24 hours in one day equals one, or just in a ratio by itself. Or, of course, you could make it look different. You could make it look like 24 hours is one day, 24 hours in one day. You could, any way you flip it, it still equals the same thing. It equals one. It actually crosses out, right? If you multiply that together, you'd be left with one. Interesting. Anyway, so going from uh, days to hours, so we have 4 days, we want hours. This is like, that's where I like to start. So we want hours, and I want to I want to be able to like cross out my days. So I know I have 24 hours in one day. That's the formula I'm going to use. I'm going to use that one. So what that means is now I multiply 4 times 24. What do I get? I get 96 hours. Is there like a movie, 96 hours or something, where guy was out in the desert for a long time? I don't know. Anyway, notice how days crossed out, you're left with hours, and that's how we're able to, when we multiply 4 times 24, we get 96, and we're able to carry the hours. Boom. So that's converted. So now using 36 hours and 96 hours, did I do that right? Or is it 90? Yeah, 96. Okay. So 96 hours. So we're going to start with 96 hours. And we're going to do the half-life of 36 hours. Boom, there you have it. So let's go ahead and carry out the order of operations. We're going to save the millicurie multiplication for later. We're going to do nothing with the half just yet. Let's get this into a decimal so we can place the exponent easily into our calculators. So let's divide 96 by 36. We're left with the answer 2.66 exponent. So let's carry out the exponent. Rewriting this would be 200 millicuries. We'll rewrite this easy for our calculator. 2.66, which is the answer is 1582. I'm going to round this to the hundredths place. So we're going to do 200 millicuries times 0.15. Now we can just simply multiply those. You notice I didn't round that completely correct. So the reason why is I'm following along with the book, and the book has 200 millicuries times 0.15. Where they got this from was not because they rounded incorrectly, it's because of what they chose to do with this. I chose to leave my 2.66 when they chose to do 2.7. So if we went back a step, we would probably get their answer. If we did 0.5 exponent of 2.7, then I get basically, so 0.5 exponent to 2.7 equals 0.1538. So if I did round to the hundreds place, that makes more sense to have 0.15. So this matters, right? Rounding fun. But I think if we carried this out to its conclusion, we can see where if this happened to you on your exam, what would happen to you. So what if I rounded at the wrong place? Is it a deal breaker, basically? So what if I did 0.16? What if I rounded that to its logical hundreds place to 0.16? What kind of answer would I get? Okay, times 0.15. And these kind of things, it seems like, why are you doing this, Lauren? Why not just get to the meat and potatoes? Well, the thing is you never know what you're going to experience on the board exam. And you want to be able to have the mental flexibility to be able to adapt to any scenario that you could possibly be given. And when you know relationships of like consequences of choosing to round to the hundreds place differently than maybe what they have calculated, you can kind of see where if your answer is a little different, you can kind of trace it back and say, oh, I probably rounded differently than they did, and then choose the most logical answer. So that's what I'm thinking is going to happen here. I think both answers are going to be very similar. And if we were given like A, B, C, D on a test, I think that I think even if we went the wrong route, we would be able to identify, the correct answer because it would be very close. Let's find out. So 200 times 0.15 is 30 millicuries, and 200 times 0.16 equals 32 millicuries. So it's possible that, they might have 32 on the board exam, and that would be pretty crappy of them. Um, but, what if they didn't? What if they had like 60, 40, and maybe 15? From 60, 40, and 15 and 30, if your answer was 32 because you rounded incorrectly and got 0.16, I think you'd probably be like, does my answer make sense? So for instance, I started with 200, which is a big. If I go to a small, which is 32, yeah, I did go from big to small, and that makes sense. How many half-lives did I have? Well, if a half-life is 36 hours, um, how many times does 36 go into 96? Well, it goes into 96 2.6 times. Okay, so that means there's about uh, one half-life. So you go from 1 to 50, right? And then you go from 50 to 25, and then you go, from 25 to not quite 12.5. So you're somewhere between 25% and 12.5%, right? Because you've done one half-life, you've done two half-lives, but the you're somewhere kind of close to the middle between the second half-life and the third half-life. So this would be the third half-life, this would be the second half-life. You're somewhere in the middle between 12.6 and 25. 25. I said 12.6, but I meant 12.5. So 2 plus. So, I would expect to be somewhere in the middle. In the middle turns out to be 18.75% percent. So, okay, cool. Oh my gosh, this is kind of a shortcut. So, holy crap. So now I know I'm at approximately 18.75% of where my initial is. Holy cow. What if I multiplied 200 millicuries times 18.75? That's basically, 18.75% divided by 100, right? To give me a number. That's my number. Well, what does that mean? Holy cow. What if, holy cow, times 0.1875? Okay, not obvious, definitely not obvious, but the number I get is 37.8 millicuries. I was wondering if I was going to get like 34, in which case I'd be like, holy crap, I could have just done that and maybe estimated. But no, I think if I were given these numbers, I probably would have, if I would have done the cheat, this simple way, the estimated way, I probably would have chose the wrong answer. So moral of the story is do the formula. I thought I found a cheat code, but don't do the cheat code because it's fallible, basically. Anyway, but I guess what the shorthand estimation, what it did for me was it helped me evaluate my answer. Is 32 less than 34? I would expect it to be less than 34 because I know that it's, 36 goes into 96 2.6 times. It's not 2.5 times. This line between the two would be 2.5. So 2.6 would be somewhere over here, which would be less than 18.75, but more than, 12.75. So long story short is I would expect it to be less than 34, but more than 32, or more than whatever. And so I would expect it to be less than 34. And since out of these range of numbers, there's nothing like 34, I think, it's reasonable to say that yes, 32 and would be a good answer. It'd be good to answer 30. It was probably just a rounding mistake, which in this case we know it was. I did 0.16 instead of 0.15. Fun, fun, fun. If you're in the exam, like you're not going to spend like these 30 minutes going over this like I do. I'm trying to like really dig deep and to show you some relationships. You're ideally you're going to kind of be comfortable with these relationships and you're going to be able to just feel good about your answers as you go through these. Or ideally you remember to do your order of operations correctly. If not, you're able to catch it because you know how to evaluate um, your answer kind of with guesstimation. Uh, we didn't go over anything with the decay constants. Nothing is given in my example about decay constants. Maybe that's just because it's not very common to go through a decay constant or experience a decay constant formula. Hmm. They do talk about mean life, and it's not about someone being nasty to you, it's about the average or the average half-life. And so the mean life is also referred to as the average life. This represents the average amount of time it takes for a radioactive atom to completely decay from its original activity. This is most useful in determining radiation dose for permanent implants. Oh my gosh! Are we going full circle? Holy shit! No, I'm just kidding. Sorry. We talked about iridium 192 being used for prostate LDR seed implants. No, iridium 192 is for HDR. But we talked about permanent LDR implants, for instance, I think, was it palladium? Um, or is it maybe, I don't remember. God bless it. But we talked about the sources and how the physicist will have to, oh my gosh, will have to determine at what point will the total dose be delivered, I think. So you want to know when the patient will no longer be radioactive, because you got to give them advice about like, okay, avoid having small children on your lap, be careful who you're around because you are slightly radioactive. Maybe abstain from sexual relations for X number of days. Like you just basically, since this person is radioactive, literally, like they need to use, a fair bit of Alara, right? And know how long this person is going to be radioactive. So the average life or the mean life is used to help understand the amount of time it takes for the radioactive source to completely decay. All right, let's just wrap this up with mean life. And it's almost going on 2 hours, so you might think I'm mean and life is mean. Mean life. Wish I was funnier. This is all right. So practice problem number 3. And I'm not, yeah, practice problem. Sorry. All right. So what is the average life for a radioactive source that has a half-life of 72 days? All right, let's read that again. And I should share the formula with you, right? So, so the mean life is TA. So mean life equals 1.44, which is, what is 1.44? Ah, okay. So cool. Times the half-life. All right. So the mean life equals 1.44 times the half-life. So that's your formula you're working with. Much easier to work with, right? Because all we need to know is half-life, which is, uh, the length of time it takes for a source to decay to 50% of its original. So let's see what it's asking, right? So what is the average life? The average life for a radioactive source that has a half-life of 72 days. Well, so we know that's also average is also mean, the mean. So that's what we want. And this is the equation for mean life. So really there's only one thing to have to plug in, and that's the one thing it gives us, right? 72 days. Okay, cool. So 1.44 times 72 days. Oh, Oh yeah. So easy. 103.68 days. I don't, how do you want to round that? I want to round it to the ones place. So we'll call it 104 days. Makes sense. It's hard to like talk about days in 0.68, although we could if we wanted to. All right. Well, there you have it. There's two formulas, really. Even though we talked about three, we really didn't use the third. The third incorporated the decay constant, and we did not find a way to utilize it while we were together. So there's formula number one, which was A equals A naught of the log of negative decay constant times half-life. Then there's formula number two, which is activity equals the new activity equals the original activity times half and to the exponent of the elapsed days and over the half-life. And then formula number three is the mean life, which is the mean life, which is TA equals 1.44 times the half-life. So really the ones we used were these two. We really didn't do much with this. All right, well, good luck. I'd like to know if you guys want some practice problems. Let me know in the email. I'm going to sign off. I know I said I was going to go over the magnification factor. We'll do that next time. If that's something you guys desire, maybe I'll make another video. You guys can tune into these videos as you like. I'd like to see you next week. Maybe you want to go through equations, maybe you don't. I'd love for you to email me, message me, and let me know what you guys want to go through. Maybe we can do something more tailored for your individual needs, as I know it's coming up on exam time. So I just want to be here to be a resource and support for you. And that's why I'm committed to spending 2 hours with you tonight, because I do want you to succeed. I believe you can succeed. I know you can do it. Set your mind to it, put the effort in, and you're way more capable than you could imagine. You can do anything you set your mind to.